Hello. So I'm just going to go through this proof by contradiction that we did in class today. I'm not going to do part B. I'm just going to work through part A just so that you could sort of see my thought process. I'm not going to use that much math, especially because I'm going to be doing some of this on Sketchpad, and I'm really bad at trying to draw with Sketchpad. I don't know. I just was trying to do it and I suck at it. So if any of you guys have done videos before on YouTube or anything and have advice for how I can make these videos better in the future, let me know. But basically we have A and B being integers. That's what it means to be in the set of Z. Z is the integers, so that means they're whole numbers. And we want to prove by contradiction that if a squared plus b squared equals 4, A and B are both even. So ultimately that statement is what we want to prove. That if we assume a squared plus b squared equals 4, and we know that a and b are integers, then a and b both have to be even. And we're using this thing called the proof by contradiction, which we've discussed in class, but I do think that a lot of us probably still need some work. A proof by contradiction is going to take this first part of the statement and treat it as fact. We're going to set that in stone. So a squared plus b squared is 4. That's definitely the case. And now we're going to take this second part, a and b are both even, and contradict it. We're going to say the opposite of that is true. So we talked about this earlier, but the opposite of a and b are both even means that at least one of them has to be odd. And a way that we could say that, I'll try to draw, is a or b, that V symbol stands for or, is in the set of odd numbers. Every integer is either even or odd, so if they're not both even, that means at least one of them has to be odd. And the professor told us earlier that there are basically 3 possibilities here. Either A is odd and B is even, A is even and B is odd, or both A and B are odd. So those are the 3 cases that we're going to have to tackle. And then the next step of this is very important. So now that we're going with this proof by contradiction, we have to assume that one of these 3 cases are true. And we're going to try to prove all of them. So I'm going to get rid of this. And let's start with the case where A is even. I'm going to type. This is a bit of a mess. So let's start with case 1. A is even and B is odd. So if this is the case, one area that I think some of us are struggling with is what does it mean for a number to be even and what does it mean for a number to be odd? And this is something we talked about last class. I think in lecture slides 5, this comes up a lot. And for a number to be even, it has to be divisible by 2. That means if you cut it in half, both halves are integers. A counterexample of this, or an example that is not the case, would be the number 7. If we cut the number 7 in half, we get 3.5 and 3.5, and those are not integers. So a way that we like to describe an even number, even means 2 times an integer. That's very important. And in the future, when we see things like an even integer, I want you guys to think of 2 times z, where z is an integer. I like to use z because z is also the set of integers. So it's a little z here. Big Z is the set of integers. So that means if in our case, where we're going to presume that A is even and B is odd, which is case 1 of 3 that we have to consider, that A is going to be equal to 2 times Z. For some arbitrary Z, that's an integer. And for B to be odd, B is 2 times an integer plus 1. And this definition is a little bit arbitrary, but it's completely correct. And this is something that also comes up in PowerPoint 5. I think PowerPoint 5b. that we could call it 2 times an integer plus 3, 2 times an integer minus 5, as long as we're taking an even number, which is 2 times an integer, and then adding or subtracting an odd integer from it. That's going to give us an odd number. And another constructive proof for this is that if you add 2 consecutive integers, that's going to create 2 times an integer plus 1, 2 times x plus 1, potentially. So we're going to represent b. It'd be tempting to call it 2z plus 1 to set b equal to that. Let's just say a equals this, and b equals, let's call it 2k plus 1. And when we're writing proofs, it's very important to put a constraint on k. K cannot be pi, it can't be infinity, it has to be an integer. So where k is in the set of integers. Cool. All right, I might just have to erase. I've never used this platform before. So now we're going to do some substituting. We have a squared plus b squared equals 4, and now we have new expressions for a and b. So we have 2z squared plus 2k plus 1 squared. And yeah, if any of you guys know how I could do this on my iPad instead and like use my Apple Pencil thing, that would be cool. Equals 4. So we're taking this new assumption from the contradiction. We're taking the contradiction, like the negation of Q. Q is this statement over here. We're taking not that and plugging in what it would mean into this. And we're going to see that we're going to end up in this area that doesn't make sense. So now if we actually multiply this, we're going to get 4z squared plus 4k squared. Oh gosh. Plus 4k plus 1 equals 4. And if we subtract 1 from both sides, we'll have this whole thing equals 3. We'll cross that out. So we have 4z squared plus 4k squared plus 4k equals 3. And this, it's important to conceptualize what this means. We know that z is an arbitrary integer. It's any number, really, a whole number. And k is also any whole number. They could be the same. They don't have to be. That's why we didn't use z for both of them, because they don't have to be the same number. So now, if we just divide all this by 4, if we divide both sides by 4, just simplifying this equation, we have z squared plus k squared. This is the aha moment. It's coming up right here. Maybe some of you guys have already figured it out, or you've looked at the proof and you know the answer. Equals 3/4. And again, we have to keep asking ourselves, what do we know about these figures here? We know that z is an integer. We know that k is an integer. Integer squared plus integer squared plus integer. This side is an integer. 3/4 is not an integer. Therefore, we have a contradiction. So this can't hold. And so this is case 1, where a is even and b is odd. Now case 2 would be where a is odd and b is even. But I think it's probably intuitive for you guys to see that this would lead us to the same exact line of reasoning, which is why in the solutions that the professor posted, she didn't actually work through case 2. She just worked through case 1 and case 3, and I'll do the same. But if you just imagine that instead of 2k plus 1 over here, we just have 2k, and here we'll have 2z plus 1 as representing a being odd. And we're going to run into the same exact thing, where you're going to have an integer on one side and a not integer on the other side. So now I'm going to get rid of, there must be an eraser on here. I just don't know how to do anything. So I'm going like this. And now we're just going to look through the case where both of them are odd, because that's, at this point, I think I've set it up enough that you guys should know how to do it, but I think it's good to see. So A and B are both odd. So let me do this. We'll call it case 3 because that's really what it is. A and B are odd. And here we'll set A equal to 2z plus 1 for some z that's an integer. And I think it's helpful to talk through these while you're doing them. And B will be 2k plus 1 for some k that's an integer. And now we're going to have 2z plus 1 squared plus 2k plus 1 squared equals 4. We're just going to plug it back into this. So A and B are being replaced by these expressions that we just made. So I'm just going to do this like, I'm not going to draw it all out because it's torture, but we're going to end up with 4z squared plus 4z plus 1 plus 4k squared plus 4k plus 1 equals 4. And here we could subtract the 1s, and we're going to get 2 on this side equals, just get rid of that and get rid of that. And so we have 2 on this side, and we're going to have 4z squared plus 4z plus 4k squared plus 4k. And similar to that first example, we're just going to divide everything by 4. And so we'll end up with z squared plus z plus k squared plus k. And we have to remember, or understand, not remember, that this is an integer because k and z are both integers, equals 2 over 4. So we just divided everything by 4. And that gives us a non-integer on this side and an integer on that side. So basically what we just did is we took the contradiction, we took the opposite of this. A and B are both even. We said no, A and B are not both even. Let's imagine that at least one of them is odd, and maybe both of them are odd. Let's look at those cases and see if this whole statement is still coherent. So could we prove that a squared plus b squared equals 4 actually implies that at least one of them is odd? And we saw that it couldn't be done. We looked at all the cases and we found contradictions in all of them where we end up with an integer equals a non-integer. We end up with that kind of form of an answer. So because none of those cases worked out for us, we have to conclude that A and B are both even. And our professor is very into doing direct proofs because they are a little more satisfying than that, where saying that not Q is not true is not quite as satisfying as saying Q is true. And so anyway, that's how you do this proof by contradiction. Hopefully this was helpful for you guys, and I'll try to do these in the future. Bye-bye.